So in this assignment, we need to prove that we are given a sequence of, sorry, we are given a sequence of and different elements, and we need to check whether they are distinct or not. And we need to show that the minimum time required is omega of n log n. We need to prove this. So the first method we are going to do this decision tree method. Decision tree method. In this, if the input is x1, x2, and up to xn, this is our input x, x1, xn. Then we can have, because we assume that all of these are n distinct, then we can have n factorial. We can have n factorial different possible answers. Now, this means that the tree should have n factorial leaves. And if the tree has n factorial leaves, meaning that the height of the tree, should be log of n factorial, which can also be written as log of n log n. So, but the problem here is that the answer we can only have it as either yes or either no. This meaning that we have only two leaves, and so the height of the tree would be log of 2 to the base to 1, which basically means is we can't proceed with this method. It's kind of useless, and we need another method to do this, to prove our claim. So now in the second method, we'll be using the concept of connectivity and convexity. So first we are going to make an claim, and then later on we are going to prove it. So the first claim is that let R of L be the instances for which leaf L is reached on execution and we assume that R of L should therefore be connected. And we are also going to make a claim that let X be a set of sequence n numbers and Y be the permutation of X only. So basically Y equals to Y1 to Yn, which is nothing but permutation of X only. So if X is distinct, that means the permutation of Y should also be distinct. So hence we must reach distinct distinct yes leaf. We are going to prove these two claims and show. If we are able to prove above both two claims, then we can also we will be successfully able to claim that number of yes leaves is greater than equals to n factorial, meaning that the time required for this, implying the time required for this is omega of n log n. So let's start with proving it. The proof of above both two claims. Let's say x equals to x1, x2, and y equals to y1, y2, yn. These 2 points, these 2 points in the region of L. Okay, so in execution 1, when we take x instance, L, a leaf L is reached. Similarly, in execution 2, when we take y instance, a leaf L is also reached, but we need to show that these two L are different. So now I'm going to take another one in execution 3 instance instance Z. We are going to prove that these two leaves are different. So let Z be from Z1, Z2 to Zn, and we are going to define Z as lambda of xi plus 1 minus lambda of yi. And the assumption is that the lambda lies between 0 to 1, implying that Z is on a straight line x y, because if the value of lambda is 0, then it means Z equals, okay, let's see. If the value of lambda is 0, meaning is that from this equation z equals to yi, just a straight line. And if lambda equals to 1, that means z equals to xi, meaning we are showing that z is on a straight line on the line x to y. But this method is by contradiction. We are using contradiction to prove. Okay, so now we have, let's take xi is less than xk and yi is less than yj. We are going to multiply this with lambda, that is lambda of xi is less than lambda of xj, and this with 1 minus lambda. So 1 minus lambda of yi is less than 1 minus lambda of yj. So If we add both of these equations, what we will get is lambda xi plus 1 minus lambda yi is less than lambda xj plus 1 minus lambda yj, which is nothing but simply the definition of z. How we define z here? Lambda xi plus 1 minus lambda of yj yi. So this is z of I is less than equals to z of j. So meaning that execution 3 will also reach leaf L. Thus R of L is convex. So now by contradiction we will say that x and y reach L, different L, whereas z is not distinct, because let's say f of w equals to w of I minus w of j. So as xi was less than xj, f of x will come less than 0, and y of I was greater than y of j, so f of y will come greater than 0. And by mean value theorem, we can say f of z equals to 0, that is vi equals to vj, meaning that z is not distinct. Not distinct means that z lies somewhere different. It is not the, if this is x, this is y, then z is not here. Z lies somewhere in the different region. Hence, we can say that the yes leaves x and y are different. Uh, mm, and y are different. Meaning that what we assumed was that it must have n factorial leaves. So we have proved there that we have n factorial leaves, meaning the minimum time required is n log n, that is big O omega of n log n. Thank you.